Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, you've come to the right spot, so go ahead and hit the subscribe button. That said, let's get into the current video. I want to talk about what are called direction fields, which is something that you will learn about at the beginning of your first semester of differential equations, usually at the sophomore level as an undergraduate. Let's go ahead and get into the idea. For a differential equation of the following form, so for a differential equation of the following form, it's a first order differential equation equal to, where I have the derivative is equal to some expression with x's and y's. This could be homogeneous, non-homogeneous, linear, non-linear. The main thing is that it has to be a first order equation where the derivative itself is isolated. Okay? So for a differential equation of that form, we can plot again, I haven't given you information on what this is yet, but we can plot what's called a direction field, which gives an indication of what the solutions look like. So I might not be able to actually solve the equation, or at least not yet, but what I'm going to be able to do is show you a graph of what the family of solutions to that differential equation will look like. Here's how we do it. At a point A, B in the xy plane, the slope of the tangent line to a solution of the differential equation is the derivative of y with respect to x evaluated at that point, but that's just going to be given by f of a, b. So what I can do is I can actually plot like little segments of tangent lines at any point in the plane. And you know, once we have a bunch of slopes of tangent lines, we can then construct what the graphs of the solutions would look like. So let's look at the following example. Let me go ahead and clean this up, and then I'll look at a specific example. Okay. Let's look at the following differential equation. dy dx equals y. Very simple differential equation. Let's take a look at its direction field, and let's see how that kind of relates to the solutions for this differential equation. Now, remember that what I can do is for any point in the plane, assuming that ordered pair is in the domain of this expression over here, I can find the slope of a tangent line of a solution at that point. And so what I'm going to do is let's pick some points in the plane. So let's say point and then slope. Okay. Now let's go ahead and list some of these. Well, let's pick some points that are easy to work with. Like let's say the point 1, 1. The slope is going to be the derivative of the unknown function evaluated at 1, 1, which remember is f of 1, 1. F of 1, 1 is just the expression that the derivative is equal to evaluated at that point. It's just going to be the y value of the coordinate, which of course is 1. Therefore, we can see a really quick way to generate these slopes. Whatever the point is, I just pick off the y coordinate. Right? So over 1, up 1, the slope is 1. over 2 up 1, the slope is 1. So we can see that anything where the y value is 1, again, the slope is 1. Let's pick some other points here. Let's say I was to pick the origin. Slope, of course, is 0. If I pick, let's say, back 1 up 2, of course, the slope is 2. If I pick something like over 1 down 2, of course, the slope is negative 2, so on and so forth. Now, what that allows me to do is actually create this direction field fairly quickly. Let's go ahead and see what that's going to look like. Let's see if this marker works. Yeah, that one works okay. All right, let's go 3 tick marks in each direction. Now remember that the slope, whenever the y value is 1, the slope is 1. That means I'm going to have a tangent line that would be, so have that slope of 1, and slope of 1, slope of 1. And let's go ahead and let's fill in as many of these as we can. And I'm going to use what I usually refer to as grid points, which means that the ordered pair has integer components. I know that on the x-axis the y value is 0, so that means I have slope of 0, 0 all along here. Do that too. Now down here where the y value is negative 1, the slope is going to be negative 1. If the y value is 2, then the slope is 2. And you can see that I'm not really doing it really accurately, which is part of one of the inherent issues with kind of creating direction fields, is how do I really distinguish quickly between a slope of 1, 2. Now up here the slope is going to be 3. Now if I were to go up any higher, slope of 4, 5, 6, 7, 8, I mean, are you really going to be able to distinguish between those? Probably not really. So therefore, again, this is just a kind of a rough technique. Made much better by certainly a computer, but by hand it will work kind of in like a 3x3 grid, generally speaking. So then down here I'll go slope of negative 2, and you can see that the way I'm kind of generating this is slope of say negative 1. Of course, at about 45 degree or negative 45 degrees, and then this would just be a little steeper and then a little steeper, and I think that's probably about as much as I'd really be able to do by hand. Now this right here, this sort of plot, is what's called a direction field. And what I can think about is if I was to pick a point, let's say I wanted to pick a point that I wanted my solution to go through, let's say roughly, I don't know, say about right here. What would the graph look like? What would the solution look like that passes through that point? Well, a lot of times what we do is we kind of add like a real world sort of interpretation to this direction field and think of it like fluid flow, like think about a stream where each of these tangent lines or tangent line segments is kind of giving an indication of where the fluid is going. Now you could see that it looks like it's going to do something like, say like that, and then of course if it's going to go in this direction, it looks like it's going to sort of taper off and kind of do something like this. Now what does that tell me about or actually let me pick one more or two more. Let's say I was to pick a point down here. It looks like sort of it would go in this direction, and then it would certainly kind of trail off this way. And then also if I picked one, say on the x-axis, well, those are all flat, so it looks like it just kind of follows along the x-axis. All right, so now let's talk about the solutions compared to the original differential equation. First and foremost, all I would know is what the shapes of the graphs look like. What this tells me is a couple of things. One, that no matter where I pick my point, the solution is going to have certain properties. It's going to have a horizontal asymptote of 0 if I go out to the left. Okay, that may or may not have sort of a real-world interpretation depending on what the differential equation represents. I also see that as we go off to infinity, there's 3 possible different behaviors. Either the function values increase without bound, they decrease without bound, or they stay at 0. Again, depending on what the equation is, that may have a real-world significance. Now, if I look at these equations, let's see roughly what they look like. This horizontal line at the x-axis, certainly that is equal to y equal to 0. Oops, sorry, that marker didn't really want to show up there, did it? I guess you can kind of see it on the board, but let me just kind of write over top of it. Y equal to 0. Now, if I look at these equations right here, or these graphs rather, what would the equation be that represents those? What's something that trails off to 0, or essentially trails off to a horizontal asymptote, and then also sort of blows up to infinity? Those look like exponential functions. So this looks like it could be, say, y is equal to, let's say, k e to the x, where of course k is going to be a positive number. What about the expressions down here, the graphs down here? What would those sort of represent? Well, those again look like y is equal to, let's say, k e to the x, where k is negative. Now, each of those three types of functions, notice that when I take the derivative of k e to the x, I get k e to the x. Well, that means that satisfies this differential equation. Name a function whose derivative is equal to itself. Well, k e to the x where k is positive, k e to the x where k is negative, or y equal to 0. All three of those satisfy this differential equation, and we can see that the direction field matches with our solutions to that. So again, before I actually learn how to solve these differential equations, we can get an idea of what the graphs of the solutions look like. We can get some properties of the solutions. Maybe they've got asymptotes, maybe they go off in certain directions, things like that. But then again, once I have my solution, we can kind of match it up to see that they are the same plots. Thank you for watching, and please consider subscribing.